SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied. Today we shall discuss about the role of a condenser in a steam power plant. If we recall, then we can understand there are a few major components in a steam power plant, and we have discussed about all those components like boiler, turbine, condenser and a pump, feed water pump. We have discussed about the boiler because boilers are essential, and this particular component is there in a steam power plant to produce or to generate steam, and steam which is produced in the boiler is taken to the turbine, and while steam is flowing or steam flows through the turbine, it does work on the rotating part of the turbine and we get work output. After doing some work, that steam is again taken to another device, that is the condenser, where steam releases heat, and again after releasing heat, steam is condensed into water, and that water is recycled back to the boiler. So, now today we shall discuss about the two important objectives or roles of the condenser in a steam power plant, and to understand that, let us again draw this schematic diagram of the steam power plant, and we shall try to map the processes in a TS plane. So, if we try to draw the steam power plant schematically, then we will see that condenser plays an important role. So, this is turbine, we get work output from this. This is the feed water pump, we need to supply some energy to the pump, and upon receiving heat, that feed water which is supplied by this pump to the boiler gets converted into steam, and that steam is taken into the turbine, not directly into the turbine. We have discussed that steam is taken to the turbine via flow nozzles. The sole purpose of the nozzle is to produce steam jets, and when steam jets impinge upon the turbine blades which are mounted on the shaft of a turbine, that turbine wheel rotates and we are getting work output. Now, this particular place, that is the condenser, wherein steam or exit steam of the turbine is taken that steam releases heat and gets converted into water, and that water is taken or pumped back to the boiler. So, now if we try to draw all these processes in this TS plane, we can see that if we consider that this particular unit is operating following Rankine cycle with superheated steam. So, that steam is superheated beyond this point, and now we can see all these processes, that is 1 to 2, this is 3, this is 4. Now, I would like to discuss first one important objective of having this particular unit in a steam power plant. What we can understand from this particular schematic is that if we do not consider this particular unit, if we consider a hypothetical case, so feed water would be pumped by this feed water pump to the boiler. Upon receiving heat from an external source, that water will be converted into steam, that steam will be taken into the turbine and the turbine will produce work. Now, after doing work, if we do not consider that that steam will be again taken to the condenser, instead that steam will be discharged into the ambient any place, then what we can do? We can understand that if we would like to discharge the steam into the ambience, then the steam will be discharged at the atmospheric pressure, and we know that steam will release heat when it is discharged to the ambience, then the saturation temperature corresponding to atmospheric pressure is 100 degree Celsius. So, what we can understand that when steam will be discharged into the ambience at the atmospheric pressure, the steam temperature will be 100 degree Celsius, and that at that temperature steam will be converted into water. Now, question is that particular process is not allowed because of this environmental constraint, because we cannot really discharge steam water mixture which is having 100 degree Celsius temperature to the ambience. Second thing, that if it is a case, then again we have to supply feed water for each time, and that is also not an economical design of the power plant. So, essentially we need to have this cyclic processes such that steam that comes out from the turbine will be taken into this condenser. Upon releasing heat, that steam will be condensed into water, that water of course saturated water, and that water will be taken back to the boiler. So, this is how this particular steam power plant works. Now, we can understand that means condenser plays a major role to convert steam into the water, so that we can operate this particular unit in a cyclic manner. So, this is one of the most important objectives. You also can understand that if we now recall the second law of thermodynamics, Kelvin Planck statement says that it is not possible to construct a device that will operate in a cycle while and produce net work while exchanging heat with a single temperature thermal reservoir. So, now let us again look at this particular schematic diagram. So, if we consider that this is only the heat thermal reservoir boiler wherein heat is supplied, we may get net work because W net equal to W out minus W in. So, even if we try to get net work output, but second law of thermodynamics puts a restriction that there must be a place where heat should be rejected if you would like to operate the unit in a cyclic manner. So, this particular place or unit should be there. So, condenser will be there if we need to run this system in a cyclic manner. So, this particular component acts like a heat sink and steam rejects heat in this particular component. So, this is one of the important objectives. Now, if we look at another one, that is the most fundamental objective of having condenser in a steam power plant. So, if we look at this TS plane, what we can understand. So, if we try to, what is this W work? This is W out. I am writing here specific work output W. So, this is specific work output, and this is H3 minus H4 that we can see from this TS plane. So, that is the enthalpy drop of steam inside the turbine and that is the specific work output. As I said you that this pump will handle only liquid. Now, if the liquid is having high temperature, then again there will be some problematic issues to handle that liquid or hot liquid by this pump, because pump blades will be, the blade material will be having certain permissible stress or thermal stress load, thermal stress bearing capacity. So, if the temperature of the working fluid is higher than the temperature which is allowed when this particular blade is selected, I mean that the blade can withstand, then if we now use this pump to handle that particular liquid which is having high temperature, blade material may fail. So, our objective should be to reduce the temperature of water which is available at the exit of the condenser. Now, if you would like to reduce the temperature of the water, then enthalpy H4 should be less, and this is also good. This is also a good thing, because higher the enthalpy drop of steam inside the turbine, more will be the specific work output. Now, consider this is this TS diagram. What we can understand that this pressure which is the condenser pressure, which is also known as turbine back pressure, the pressure at the exit of the turbine. Now, if this condenser pressure is atmospheric pressure, say for example, then the liquid, saturated liquid at point 1 that would be available at the inlet of the pump will be having temperature 100 degree Celsius temperature. So, basically we can understand that if we do not have this particular unit condenser, and by any means if we try to condense the steam at the atmospheric pressure or atmospheric condition, then temperature of the liquid or saturated liquid that would be available at the inlet of the pump will be having high temperature. So, that temperature will, I mean the liquid with that high temperature will be or will create a few problematic issues to run the pump in a long run. Second thing, I mean if we still use any device wherein steam will be condensed into the liquid at the atmospheric pressure, then you can understand that temperature or enthalpy at state point 4 will be relatively high, and that if that enthalpy is high, then this enthalpy drop will be reduced and specific work output will be reduced. So, the ideal situation should be that the liquid temperature, which is the temperature of the liquid at the inlet of the pump, should be in the range of 25 to 30 degrees Celsius. It may also be 20 degrees Celsius. Now, if we consider that the liquid temperature, that means the temperature of the liquid at the inlet of the pump should be 25 or 30 degrees Celsius temperature, and at 25 or 30 degrees Celsius temperature, saturation pressure is way less than the atmospheric pressure. And so, this is when P atmospheric, we know that is 100 kilopascal, I mean close to 100 kilopascal. So, if we now reduce, so basically 101.3 kilopascal or 100 close to 100 kilopascal. So, now I can write like this. So, at that pressure, temperature of water would be 100 degrees saturated temperature. So, we need to reduce the temperature of the water at the inlet of the pump. So, and that would be 30 to 25 or 30 degrees Celsius, and at that temperature saturation pressure is much less than atmospheric pressure. Now, at 20 degrees, at 25 degrees Celsius, P saturation is 3.16 kilopascal. So, you can understand that is significantly lesser than the atmospheric pressure. So, that means the entire condensation process will be conducted at a pressure which is way less than the atmospheric pressure, and if we need to perform this particular process, we need this particular component, and that is the condenser. And if we do like this, then try to understand, say this is the pressure. So, now this is 1 prime. So, temperature of 1 prime, you can understand that T1 prime is less than T1, and the corresponding saturation pressure also will be less, and not only less, this is substantially lesser than the atmospheric pressure. So, this would be good for the power plant, because you can understand now this point should be 4 prime. So, you can understand that the specific work output will be more, because H4 prime is much less than H4. So, we will be having high enthalpy drop. That means, if we can design the system in such a way that the entire condensation process or entire this phase change process, that steam will be converted into saturated liquid in a condition where pressure will be substantially less than the atmospheric pressure, we can understand that the specific work output will be more, because enthalpy drop will be more. H3 is fixed. So, H3 is equal to constant for this case, right. So, now since the pressure is way less than the atmospheric pressure, we need to have a special device that will operate at this pressure, and this is what is done in a condenser. So, we can understand condenser is not only condenser is having two different or two important objectives. First of all, it allows the entire unit to operate in a cyclic manner. It also allows to reduce the turbine exit pressure or back pressure of the turbine, so that the total enthalpy drop will be more, specific work output will be more, and also the temperature of the condensate at the exit of the condenser should be near about 25 to 30 degree Celsius temperature, and then pump will not be having any problematic issues to handle that liquid. So, these two are the important objectives. So, if I write, so the role of a condenser, number 1, it is number 2 is so these two are the major objectives of the condenser. So, it allows to operate the entire unit in a cyclic manner. It also allows to reduce the turbine back pressure, that is the exit pressure of the turbine, and which in turn allows to have more specific work output. So, now if we look at the different types of turbine, so there are two broad classes of condenser. So, we have talked about condenser, and there are two broad classes. The first type is direct type, and second one is surface type. So, you can understand from the classification, it is from the name of the first type, that is direct type. So, what we can understand from this schematic depiction is that in the condenser, steam will be condensed into the saturated liquid, and that means the flowing stream will release heat, and for that we need to have one cooling medium. So, that means in this particular unit, if we try to draw this unit again, so this is the condenser, and in this condenser steam will, so this is stream that comes out from the turbine, exit, and we will be getting at the exit of the condenser, that is called condensate, saturated liquid because we would like to use pump. So, this is the saturated liquid. Now, this process is basically a heat exchanging process. So, that means we need to circulate coolant, and this is coolant in, and this is coolant out. So, basically this is the condenser. So, this is the condenser, condenser is a type of heat exchanger in which two different streams exchange heat. Now, the flowing stream can be allowed to mix with the coolant directly. If it is the case, then it is a direct type condenser. If we allow coolant to flow through the tubes and steam will flow over the tubes, so the two streams will not be allowed to mix directly, that is the surface type condenser. So, as I had written here, direct type, that is two streams will be allowed to mix together and eventually at the exit of the condenser will be getting a single stream. It is designed accordingly, so that the amount of steam after mixing with the coolant will be produce the saturated liquid. Second thing, which is surface type, in which two streams are not allowed to mix together, rather from the convenience of maintenance and cleaning purpose, we need to flow coolant through the tubes, while stream will flow over the tubes, and in the process heat exchange will take place and steam will be converted into saturated liquid. So, this is called surface type. So, now so I am writing here direct type, that means two streams, that is steam and coolant mixed together and at the exit single stream comes out at the exit of the condenser, of course. So, this is direct type. Now, let us discuss about one particular direct type condenser, just for the sake of understanding how this particular type works. So, surface direct type is one there are different types available in the category of direct type. So, one particular type is spray condenser. So, if we try to draw the schematic, then so this is the condenser. This is the pump and this is dry cooling tower. What is done? Let me tell you, steam that comes out from the turbine, steam at the exit of the turbine is taken into this condenser, this is of direct type, and what we can see that steam flows through the condenser and in the flowing steam this water is sprayed. So, this is water spray. So, water is sprayed into the flowing stream, and as if these two streams are now mixing together, eventually we will be collecting condensate. So, this is the condensate. Now, that condensate is again pumped back to the dry cooling tower, and that water is again sprayed into the stream. Part of that condensate is pumped to the boiler as the feed water. It is very important. So, if we consider this is 0.1, this is 0.3 and this is 0.4 and this is 0.2. So, you can understand, as I said you, that the condensate after collecting in this basin, that condensate will be pumped and a part of that condensate will be pumped back to the boiler as the feed water, and the amount of that feed water will be equal to the amount of steam, while remaining condensate will be pumped back to the dry cooling tower. Herein again that condensate will having relatively higher temperature, and that condensate will release heat to the air, and that after releasing heat, that condensate will be again sprayed into the flowing steam. So, this is a continuous process. So, if we try to have a simple mass and energy balance analysis, then we will come to know the amount of water that is needed to be supplied per kg of steam to get the saturated liquid at the inlet of the pump. So, if we write mass balance, what we can write? As I said you that mass flow rate of steam should be equal to mass flow rate of feed water. So, m dot 4 equal to m dot 2 and m dot 1 is essentially m dot 3 plus m dot 4. So, m dot 1 equal to m dot 3 plus m dot 4. So, this is the mass balance, and if we write the energy balance, so if we go for the energy balance, then we can write what we can write enthalpy of the steam that is available at the inlet of the condenser plus enthalpy of the coolant that is available at the inlet of this condenser. So, the total enthalpy or total energy at as if we are trying to have the energy balance energy balance across this condenser. So, we can write this m dot 4 H4, that is the total energy available with the flowing stream, m dot 3 plus m dot 3 into H3. So, this is the energy available with the flowing steam, this is the energy available with the flowing coolant equal to m dot 1 into H1. So, that is the total energy which is available with the condensate that is collected in the basin. Now, m dot 1, if we go to the previous slide, we can see that is m dot 3 plus m dot 4. So, this is m dot 3 plus m dot 4 into H1. So, this is what we can write here. So, this is the quantity. Now, we can now calculate m dot 3 divided by m dot 4 equal to H1 minus H4 divided by H3 minus H4, right. So, this is m dot 3 divided by m dot 4, H1 minus H4 divided by H1 minus H3. Now, if we can that is what we can write. So, that is we can write H4 minus H1 divided by H4 minus H3, H4 minus m dot 4, m dot 3 divided by m dot 4 equal to H1 minus H4, H1 minus H4 divided by H3 minus H1. So, it should be H1. So, this should be H1. This should be H1, right. Now, if we go back to the previous slide, we can understand that H4 minus H1 is much higher than H3 minus H1, because steam is having high enthalpy than the enthalpy available with the coolant at the inlet of the condenser. So, that means what we can see, H4 minus H1 is greater than H1 minus H3, right. So, that is H1 minus H3. Certainly, enthalpy of the condensate will be higher than the enthalpy of the coolant which is available at the condenser in, because that coolant will take away certain amount of heat from the flowing steam. So, we can understand that m dot 3 should be greater than m dot 4. So, that is what I was discussing few minutes back, that this particular unit will be designed in such a way that the amount of coolant flow will dictate, I mean that the condensate which would be available at the inlet of the pump should be saturated liquid. Now, coming to the surface type heat exchanger, surface type condenser, as I said you that the condenser is a type of heat exchanger. So, it is a surface type heat exchanger. Now, if we try to recall surface type condenser, because of this name, so we are not allowed to have, or rather it is designed in such a way that two streams will not mix together. Two streams will be exchanging heat I mean while they are passing through the condenser without getting mixed. So, if we now draw the schematic of this particular type, So, what we can see from the schematic is that coolant is taken through the tubes. Basically, I am writing coolant because coolant may be water, it may be any oil. In most of the cases coolant is water. That coolant flows through the tubes and steam passes over the tubes, and when coolant, since the coolant is having low temperature, so the tube surface is having low temperature. When steam passes over the tubes, when steam is in contact with the cold surface, it condenses, and eventually we will be collecting condensate here, right. So, you can understand this is a mechanical arrangement, the tube which is shown at the top. So, coolant is allowed to flow from right to left or left to right, that is depending on the design. So, coolant is, so this is in this direction and this is the flow direction. So, you can understand this is called two pass surface type condenser, as if the coolant which is entering into the tube at the top passes from right to the left, again there is a bent tube, and through this bent tube which is connecting the top and the bottom tubes, that coolant again passes from left to the right and eventually it goes out. So, this is called two pass surface type condenser. Now, it is not mandatory that always condenser will be two pass condenser, but single pass condenser is also fine. In case of a single pass condenser, this tube will be having one inlet and one outlet. So, tubes are not connected by using this bent tube. So, there may be even two tubes for a single pass condenser, but coolant will flow from the right to the left and it will goes out. Now, question is, in this case we can understand that coolant when passes through the tube which is placed at the top, when it is coming out from the condenser, again taken to the condenser through another tube, and finally it comes out and it is taken for further heat exchange purpose. So, question is, in this case we can understand that there are two boxes available. One box is placed at the right and this is called divider. So, this divider is given so that the coolant in and coolant out do not I mean this, when coolant is coming from the external source, that coolant will be having low temperature. So, this coolant will not be allowed to mix with the coolant which is going out from the condenser, and that is why this divider is given. And this left box is provided to accommodate this bent tube. You can understand there are several this we need to hold the tubes inside the condenser. So, mechanical arrangements will be there, and this is called steam dome. Now, this particular design is because we can understand that as if we are allowing steam to have more or less uniform distribution when it flows through the condenser. If we do not provide this particular shaped part, then steam will be having almost non-uniform distribution, and then the tube, the part of the tube which is which is adjacent to the condenser side walls will not be in a position to be in contact with the steam, and heat exchange, the performance or efficiency of the heat exchange or heat transfer will be reduced. So, this is a surface type heat exchanger, and this is most widely used condenser in a power plant. So, direct type condensers are not widely used, but surface type condensers are most widely used in the power plant. Now, I would like to discuss one important point here, that instead of two pass condenser, if we use single pass condenser, then there will be an important benefit at the cost of some one again disadvantage that I would like to discuss. So, if we now write that is 2 pass, that is what we can see vis-a-vis single pass. As I said you, for the single pass coolant will come in and go out, coolant will not be again directed into the condenser using this bend tube. So, 2 pass if we now consider, so now if you are trying to compare the performance of 2 pass condenser vis-a-vis single pass condenser, we need to have a common basis. So, basically if we fix number and size of the tubes are same. So, this is 1 and flow velocity is also same. So, if we consider that number and size of the tubes will be same, velocity of coolant when passes through the tubes will be the same, then the amount of coolant needed for the single pass will be just double than the amount of coolant needed for the 2 pass. So, let me tell you once again, if we keep the number and size of the tubes are same, if we consider the velocity of coolant when passes through the tube is same for both cases, then the amount of coolant that will be required for the single pass will be double than that is required for 2 pass condenser. So, this is the disadvantage, but the advantage is for a single pass rise in temperature will be even half of the coolant than the 2 pass. If the rise in temperature of the coolant is even less, then we can reduce the turbine back pressure, we can reduce the condenser pressure, and if we can reduce the condenser pressure further, if we look at the schematic depiction this TS diagram, then we can understand that the specific work output will be more. So, this is the difference between 2 pass and single pass condenser. So, this is the if I now box it, then this is the disadvantage. Why this is disadvantage? Because if we need more coolant, then the pumping power will be more, right. So, this is the disadvantage. Now, the advantage is for single pass rise in coolant temperature will be half than that the temperature so the rise in coolant temperature will be half. So, basically if the rise in coolant temperature is reduced, we can again lower the back pressure, right. because saturation temperature, try to understand again. So, essentially we will be getting saturated liquid. So, if the rise in temperature is reduced, that means the saturation temperature will be reduced. So, we can go further or lower back pressure. If we reduce the back pressure or condenser pressure, specific work output will be more. But let me tell you one important thing, maybe we can reduce the turbine back pressure or condenser pressure, or we can lower the condenser pressure further and further to get specific work output, but we will be having another important disadvantage, that the point this particular point, that is the turbine exit, that particular point is now going away from the saturated vapor line. That means the steam quality at the exit of the turbine will be having high moisture content. So, it will be having again the problem will be there from the perspective of turbine blade erosion. So, though we can increase the specific work output by lowering the condenser pressure if we use single pass condenser, because temperature rise will be less, but the turbine exit, the quality of steam at the turbine exit will be poorer and turbine blade erosion problem will be there. So, this is the comparison between 2 pass and single pass condenser. Now, finally, I would like to discuss one important point, that is if we look at this particular type of condenser, what we can understand that from today's discussion, that condensers play an important role from two different perspectives. First of all, it allows to run the unit in a cyclic manner, and also it allows to operate the turbine at a low turbine back pressure, that is the specific work output will be more. But the question is, we can understand that if you would like to have coolant available at the inlet of the pump, will be having temperature maybe 25 or 30. So, the saturation pressure at that temperature already I have mentioned that it is way less than the atmospheric pressure. That means the entire unit will run or operate at a pressure which is way less than the atmospheric pressure. So, though all these parts are connected through mechanical components, since the unit is running at a pressure which is way less than the atmospheric pressure, air leakage problem will be there. So, air will leak into the condenser through different joints. Also, there is a possibility that when steam is coming out or steam comes out from the turbine, that steam is having some amount of air which has already leaked into the steam through the turbine flange or flanges. So, when steam is having air already, and also steam will also air will leak into the condenser, because condenser pressure is much less than the atmospheric pressure, that air will be having or will create two problematic issues. One is when steam is in contact with the cold surface of the tube, steam will condense, but since air is non-condensable, that air will create a thin film around the steam surface, tube surface. So, it will reduce the heat transfer capacity. So, air is non-condensable, steam will try to condense, but since air is not condensable, air will create a thin film over the tube surface and it will reduce the heat transfer capacity, because air is having low thermal conductivity. Number 1. Number 2 is, so this is very important point, and if by if air leaks into the condenser through different joints, then the vacuum pressure will be reduced. So, the pressure at which condenser is operating will be reduced. So, that means the turbine back pressure will be reduced and turbine work output will be reduced. So, if air leaks into the condenser and then the pressure inside the condenser will be again go up, which in turn will allow or reduce the turbine back pressure and will reduce the enthalpy drop. So, turbine specific work output will be reduced. So, these two are the problematic issues because of the air leaking, because of this air leakage into the condenser. So, air removal arrangement should be there. Not only air can leak into the condenser through the joints, but also some air will come with the steam stream itself, because already air has leaked into the steam at the turbine exit through turbine flanges. So, air removal part also should be there, otherwise it will create the problematic issues that we have discussed today. So, with this I stop here today and we shall continue our discussion in the next class. Thank you.